and then we're going to get on to psychrometrics. So thanks, Jock. You've started recording.
Yep.
So, morning, Stephen. Yeah,
Good morning.
heat loads first, and then we'll get on to psychrometrics. I'm not going to try and tackle all that today. I think it's a bit too much to try and get through and to have time to ask questions. So I'll share my screen. Okay. So can everyone see that, the notes? Okay. All right, so I'll just start reading the notes, and I'll put up some slides as we go through and talk about those. So heating and cooling loads, fundamental requirement, and I'm sure you've all had some experience already with these. Air conditioning, the process of removing or adding heat in a building to provide comfort for occupants. That's pretty much what we do every day of the week. Occasionally, you'll get involved in more complex projects, which is providing consistent and stable conditions for process control, laboratories, storage rooms, archives, that sort of thing. And that's a lot more technical, but very interesting projects. And ventilation, removal of unwanted odours, dust, fumes, etc., and provision of outside air for comfort, health, for occupant health and comfort. So what exchange occurs in buildings? It's basically a heat transfer process. In the cooling cycle, heat enters a building or a space from external and internal sources, causing the indoor temperature to rise above the design temperature. External heat sources include solar radiation through windows, glass doors, skylights, etc. We have direct and diffuse radiation. So direct radiation is when the sun is coming straight through the glass, and you can feel it. You can feel the radiation hitting your face, hitting your body. And diffuse radiation, which is, even when it's cloudy, you're still getting diffuse radiation. So, and that's sometimes called sky radiation. And reflection from clouds, etc., will still bring heat into the building. That's called sensible heat. Does everyone know what sensible heat is? Sensible heat is basically by virtue of a temperature difference. Okay. Heat conduction through walls, roof, floor, windows, etc. So windows again, we've got conduction, which is sensible heat by virtue of a temperature difference, whereas solar radiation is, as it says, radiation. Warm outside air intake. So in the cooling cycle, it's hot outside. You've still got to bring outside air in for ventilation, and that's got sensible and latent heat. So the cooling coil that has to remove the heat has to deal with the temperature, reducing the temperature and reducing the humidity of the air. In infiltration or leakage of warm air into the building, and again, this is sensible and latent heat. So you've got cracks in the fabric. I mean, if it's a new building, they're pretty well built these days and you don't have much leakage, but older buildings, through gaps around windows, cracks in the building, you will get infiltration, air coming in under doors and things like that. We've also got internal heat sources, heat output from lights, which is sensible heat, and people, which is sensible and latent. So people are giving off moisture. We're evaporating it. Air's being evaporated from our bodies. So that's putting latent heat into the space. Heat output from internal machines like computers, printers, other equipment, photocopiers and so on. That's sensible heat as well. Transmission through internal walls and partitions is sensible heat. So if you've got say you're in an office space and you've got an unconditioned space adjacent to where you are, which might be for storage room, might be say a room with printers in it, which generates a bit of heat and it runs at a higher temperature, then you're going to have some heat transmission through the wall. And estimating the temperature difference between those two rooms is really just whatever you think it might be. It might be half the difference between inside and outside, but you'll have to use judgment to work that out. So on the heating cycle, heat leaves a space due to a lower temperature outside the building, causing the indoor temperature to fall below the desired point or design temperature. When calculating the heating load, we don't usually worry about latent heat transfer. Sources of the heat loss include heat conduction through walls, roof, floor, windows, etc., by virtue of temperature difference. So once again, that's sensible heat, cold outside air intake, ventilation, and again, infiltration of cold air into the building, all creating heat loads or heating loads. Design criteria. So to start the process, we need design criteria for the air conditioning systems. Now, this will include design internal and external environmental conditions, temperature, humidity, as well as the thermal performance details for the building fabric, for the walls and windows and roof, floor, and so on. Now, quite often, I'll come to that in a sec, outside ambient conditions for summer temperature, winter temperature, relative humidity. This may be specified or is available in the Air Handbook or CAML program for the project location. We're going to talk about CAML a bit more later, but CAML is the software we normally use for calculating heat loads. And that has temperature data for many locations already built into the program. The Air Handbook, I'll just bring that up. This is a page 24 out of the Air Handbook. This is the 5th edition. This gives the tables of ambient conditions for different locations throughout Australia. So I've highlighted Melbourne. And comfort or non-critical processes is basically an office space, residential apartment, spaces that are just for comfort of people. Critical is for processes that must be controlled accurately. And for example, a hospital operating theatre would come under critical. And you've got the winter conditions as well. So for Melbourne, there's dry bulb temperature 34.3. These are temperatures that are not exceeded or 10% of the time, basically, I think is how they work this out. Now, this column on the left of that, CWB, is the coincidental wet bulb temperature. So 34.3, the coincidental wet bulb is 19.4, or the highest wet bulb, or 90% of the time, is 20.5 degrees, and the coincident dry bulb is 32.3. The usual design conditions for Melbourne are taken as usually 35 dry bulb, 21 wet bulb. That's what we would normally use. So inside design conditions, but as I said, those conditions will be in CAML. You can change them in CAML if you want to, or if there's a need to. Or if you can't find them in CAML, you might have to get some data for the local area. If you're working outback Queensland or something, you might need to do a bit more research to get that data. Inside design conditions for summer and winter may be nominated in the specification or design brief. If there's no brief or spec, we can nominate conditions based on the type of space and area guidelines. So here's a guide. For an occupied space, we would normally nominate 24 degrees and 50% RH for summer and 21 degrees for winter. Relative humidity is not normally specified for winter, and we'll come to that later under psychrometrics. Obviously, the higher the temperature that you select in summer and the lower temperature in winter is going to be beneficial for energy savings, but it's also got to be a comfortable situation where people can actually work. In an office space, you're sitting there, you're not moving around very much. So if you run it too cold, or it's really a waste. You don't need it to be so cold. I know up North Queensland, they like to run the air conditioning at 21 degrees all year round, which is a terrible waste of energy and causes condensation on walls, etc. So I've got a psychrometric chart here now. I don't know how much experience you've had, but we'll come to this in the next session. But this shaded zone here, can everyone see the psych chart? Just didn't nod yet. This is for summer, indicative summer comfort zone. And it goes from 22 degrees dry bulb up to 27 degrees dry bulb at various humidities. Well, obviously at 27 degrees dry bulb and 60% RH, that's getting a bit uncomfortable. The star that I've highlighted in the middle here is the normal conditions we'd select, which is 24 dry bulb, 50% RH. But anywhere in that shaded area is considered to be comfortable under certain conditions. In winter, we go a bit lower than that, and we'll come to that later as well in the next session. Specialised areas like laboratories, archive storage, museums, operating theatres, etc., normally have very stringent conditions for requirements for internal conditions with close tolerances for temperature and relative humidity. So they might say a laboratory or archive storage might require 20 degrees or 21 degrees dry bulb and 50% relative humidity, but with very close tolerances, plus or minus even 2%. And also pressure differentials and air change rates are critical for those sort of areas normally. But once again, that'll be specified in the design criteria, or you might have to do some research, talk to your clients and find out what they need. And ventilation, the design brief may specify a requirement for ventilation rates for the various processes being carried out in the building. Excuse me. The basic requirements will be for outside air and exhaust removal, like toilet exhaust. And they must comply with those 1668 Part 2. So if the design brief specifies something that doesn't comply with those 1668.2, that needs to be clarified. But really, that's the guiding factor, and the NCC. It'll have occupant density in people per square metre or the actual number of people. It's better to get the actual number if you can. So if there's a drawing that shows a seating plan, use that rather than people per square metre. It'll have the lighting types and intensity, watts per square metre, or the actual total watts for the area. It'll have internal loads from computers, printers, photocopiers, etc. Again, watts per square metre or total watts. And then the building external construction materials. Now, this may or may not be in the design brief, and it's something that you're going to have to find out from architectural drawings and from asking questions if there's insufficient information. So we need to, well, before we just discuss that, I'll just show you a sample of design criteria, which I've taken from a project that we're involved in. So I've blanked that out to protect the innocent. Air conditioning systems. So here it gives design outdoor ambient conditions. It's taken those figures for summer straight out of ERA and winter, and they've nominated 80% RH in winter, which really doesn't mean too much, but we'll talk about that in psychrometrics. In internal design conditions, this is an aquatic centre actually, so it's It's not an office space, but summer, 24 plus or minus 1.5 degrees. And they're saying 60% maximum relative humidity. But by virtue of cooling coil performance, that's a common thing to say. And what it means is that there's no humidity control. They're just expecting to get 60% RH based on their selection of a cooling coil. Okay. In winter, 21 degrees plus or minus 1.5. So in winter, that's saying that the control range could go down to 19.5 degrees, which is probably quite okay. It's getting a little bit cool if you're sitting around in an office space, but if you're moving around, it's probably not too bad. And then there's other areas within the same complex for internal design conditions. These are some of the air-conditioned spaces and the heated spaces. Design populations. Now, this is really important to get this right. For an office space, it's pretty straightforward.
Can I just ask a question about the coils and the RH point where you said without controlling the RH, controlling it would be basically, and correct me if I'm wrong, playing with the thickness of the coil to either capture more moisture or not. Is that correct?
Yes, correct.
Okay.
Yeah.
Okay.
Yeah, but it also requires having humidity sensors so that you can work the coil to achieve the dehumidification you're looking for. They're not asking for that in this case, and normally they don't, unless you're working on a critical process such as a lab, archive, storage, museum, those sorts of projects. Then you will need humidity control.
Okay.
Right. Now, occupation. Yeah, as I said, for an office space, residential apartments, it's pretty straightforward. But for more complex spaces, sometimes you need to do a bit of research and discussion to really determine what is going to be the design occupation of the space. I worked on a museum a few years ago. This was a really difficult thing to resolve because, you know, at first they said, oh, there's going to be 5,000 people in the museum. Whoa, that's a lot of people. And then we looked at a number of different references to try and determine what the occupation would be, because nobody really knows how many people are going to turn up. But it turned out that the fire engineering brief for the project had based their design on a certain number of people. And in the end, that's what we used. It made sense, and basically the museum was licensed for a certain number of people. Say it's 1,000 people. That's the maximum number of people that can be in the space at one time to ensure that it's safe in the event of a fire. So that made sense. So that might be a reference you can go to if you've got difficulty determining the design occupancy. Excuse me. Outdoor air ventilation. Says here, AS 1668 Part 2 requires a minimum of 10 litres a second per person. However, this can be reduced to 7.5 if the outside air is adequately filtered in accordance with AS 1668 Part 2 Appendix D, which gives you guidelines on filter selection. Basically, it's got to have an efficiency greater than 20% on test dust number 1, which brings you back to G4, F5 type filters. Then it talks about pool hall ventilation. So we won't go through all these. Toilet, shower, exhaust ventilation, general exhaust ventilation. All of these things come out of AS 1668 Part 2. Plant rooms, 5 litres a second per square metre, etc. General storerooms, the same. Kitchen exhaust ventilation, again, AS 1668 Part 2. And then they talk about CAML. The calculations have been based on, they've done some preliminary calculations using CAML, This is what they allowed for people. This is what they allowed for lighting, etc., etc. And then when it comes to external fabric details, these figures are basically out of the NCC. So they've allowed an R value, total resistance of 3.2 for the roof and ceilings, external walls, etc. Glazing, they've allowed a U value of 3 and a solar heat gain coefficient of 0.4. So that's an example of some design criteria, and it's important when we get to the end of a project. We talked about this in the last program, is when you're putting together the maintenance manual for a project, is to put in to the manual the design criteria for the project, because that can be useful if somebody questions something down the track and says, oh, the temperature in here is 24 degrees. Well, okay, that's what it was designed for, but they might want it to be 22. So those things do come up, and so you need to document that. Okay, so getting back to building external construction materials, we need to determine the fabric data for use in the heat load calculations. And we need at least the following information: external wall construction, including colour, insulation, internal finish. With this data, we can calculate the U value. Does everyone know what a U value is? Okay, it's the overall heat transfer coefficient.
Yeah.
You'll find this again and again. This will come up, and I'll show you an example in a second. And the Q, which is the heat transfer conduction, is U times the area times the temperature difference. So if you're talking about heat transfer through a wall, you calculate the U value, you look at the area of the wall, and you know the delta T. Now, this is a bit more complex than this. I'm just giving it a simplified version. There isn't what they call an effective delta T, which takes into account solar radiation. Because the sun is shining on a wall, it's going to warm up during the day. So that it's not just the temperature difference between outside and inside. There's there's a build-up of heat which is going to have an effect on that effective delta T. But just be aware of that. That's taken account into CAML anyway, so you don't need to calculate that. Now I'll just go back to the technical handbook and go and show you some so these are some typical overall heat transfer coefficients. These are for masonry walls. And this is really showing you how to calculate the U value. That you sum up the resistances of each element. So you've got an outdoor airfill, which creates like a boundary layer on the outside. Then you've got the wall construction. You might have air gaps, then indoor plaster or plasterboard, and an indoor air film, which again is a boundary layer. Get a total resistance, and you take the reciprocal of that to get the U value. So there's lots of examples for different types of walls. And then we go to, these are floors, and there's roofs and so on, different types of roofs. Now, all these things are in CAML. CAML's got a huge amount of, a big library of all these U values. If you can't find one in CAML, then you need to find out what the construction is by looking at the architectural drawing sections and calculating the U value. And that's the way you go about it. Sometimes you have to do that. External glazing, U value and shading coefficient or solar heat gain factor. This data will either be specified or provided by the architect or builder. Now, sometimes you have to ask for that because they haven't told you, and maybe they haven't decided yet, but it's crucial for your heat loads to know what that is. If there's any skylights, they have a U value and a shading coefficient. Roof construction should be available from architectural drawings. The insulation and internal finishes Again, calculate the U value or select it in Camel, and the same with the floors. External glazing is often the dominant factor in heat gain or loss in a building. Now, if you've done some heat loads, you'll know that. The glazing is crucial. It's important to ensure that the performance data is correct for the proposed glazing to enable the most accurate heat load calculations. Lower values of the U value and shading coefficient will result in lower heat loads. So when you're consulting with a client, they're the sort of things that are important to talk to them about, is what sort of glass they're using. And if they're looking for energy savings or capital cost savings on the equipment, changing the glass can make a huge difference. Right, now moving on, concept design. So we've got the design criteria. What sort of system are we going to put in this project? In Camel, it does ask you to fill in this data for the type of system that you're going to use. So some examples are DX split systems, could be ducted or non-ducted, or packaged units, VRF DX distributed systems, local fan cool units with chilled water and heating water, or central air handling units with air ducted to the zones with maybe VAV boxes and chilled and heating water. And Camel will then calculate, well, you need to nominate the chiller and boiler circuits, obviously what fan cool units are connected to what circuits, but if you've got one big chilled water and one big heating water circuit, well, they're all connected to the same circuit. And at the end, Camel will tell you what the total capacity is and any preconditioners that you're using. So you may have to use preconditioners for outside air, and which is determined in the NCC, depending on the airflow rates. Or you might just choose to use one in a central air handling unit. Thermal zoning. The air conditioning systems in a building are often designed to cater for various temperature controlled zones, which we just call zones. An example of a typical zone is given below. Office building, typical zones would be centre, internal, west perimeter, east perimeter, north perimeter, south perimeter, perimeter being the external fabric of the building. The perimeter zones are affected by fabric loads due to solar radiation and conduction through the building fabric. This is the walls, windows, roof, and floor if it's exposed. So I've got a diagram of a very simple zoning setup. North perimeter zone, and normally we allow 3 to 4 metres in because that's how deep an office is going to be. Usually they build the offices on the internal zones, no, perimeter zones, sorry, so that people have windows, they can look outside, and they're going to have partitions built in here to separate that from the centre zone. The only thing that's influencing the centre zone is the internal loads. So people, lights, any internal equipment. If there's a roof over this area, all of these zones will be affected by the roof. In this particular case, this is not a real project. I just got this off the internet, but there's a wall between this main area and the east zone. So they've called the whole thing an east zone. And I've added these figures 3 to 4 metres. If that zone there was, say, 10 metres or even 5 or 6 metres, you might have to consider having an internal zone and a perimeter zone for that space. Okay, because the solar load and the fabric loads only affect so far in. You need to use some judgment on that. Right, now let's get on to heat loads. Air conditioning is not a precise science, but it is necessary to estimate the loads as accurately as possible to provide human comfort or consistent conditions for specialised processes. During the very early or schematic design phase, it's often useful to make a preliminary estimate of the expected heat loads to assist with spatial allowances for plant rooms and risers, etc. So I don't know whether you've experienced this, but quite often when you start a project, The builder or the architect will ask you, what size risers do you need? And you haven't even started doing heat loads yet. So you think, well, how are we going to work that out until we do the heat loads? So the heat loads do take a bit of time. So ERA's got some check figures, cooling load check figures, which are useful at this early stage. But obviously the detailed calculations need to be carried out to get the right answers. But so I've got some check figures here to show you. Don't know if you've seen this. This is quite handy. So let's have a look at an office space, for instance, down here. Interior spaces, 100, which, as I said, is just the internal loads, people, lights, and equipment. General perimeter is 170 watts per square metre. So that's making an allowance of 70 watts per square metre for the heat load through the fabric, through windows. These are only averages because every building's different. They'll have different glazing, different amounts of glazing, and so on. For a private office, it's 180. Now, private, that might mean that it's on a corner. So they've got glazing on two sides. For an apartment residence, 120 watts a square metre. You might be asked to do a shopping centre and make an estimate of what the load's going to be. So there's a few areas here. There's cafeteria, 350 watts a square metre. There's hairdressers, beauty shop, clothing store, etc. Computer rooms. You might have a computer room, and so actually when you do a computer room or a data centre, it can be very difficult to get the heat loads of the space. The main loads are obviously all the computers in that room because there's no windows. It'll be a well-insulated building. So you've got to work out what the heat load of that space is, and it could range up to 1,000 watts per square metre. I have experienced that. So just be careful with those because they have very high loads. They also have very stringent requirements for temperature, humidity, and so on. Years ago, I was working on a resort project, a hotel and resort facilities. And a young engineer was assisting me with it and did the calculations on Camel and came back with the results and was very pleased. It was all done and showed it to me, and the load was 1,000 watts per square metre, and that comes up on the front of your Camel calculations on the front page of your output. You'll see that, and I said, well, it's wrong, and he said, well, why? How do you know that? And I said, it can't possibly be 1,000 watts a square metre. Why not? It can't. It's not going to happen. And so if you're aware of these sort of figures, you can see that there's nothing near 1,000 watts a square metre except a computer room, perhaps. So it's a good idea to look at that when you finish your calculations. If you're doing an office and you get an overall figure of, say, 130 or 140 watts a square metre or something, you think, well, okay, we're in the right ballpark. But if you get something like 400 watts a square metre, something's wrong, which usually means you've got something wrong in your input. And in the case of that resort that I mentioned, the young engineer had put in, I can't remember exactly what it was, but like 100 watts a square metre for lights or something like that. And we found that it was changed, and then we got the results we needed. The calculation of heat loads requires collection, measurement of a lot of data relating to the building and the proposed air conditioning system, and then entering that into the program. In this case, we're talking about Camel. That's normally what we use. There are other programs available, but Camel is Australian. It's recognised very widely throughout Australia and accepted. Training and support is available online, and there's the website there. Camel, the ACADS people used to run face-to-face training, sometimes twice a year. They travel all around Australia. They don't do that anymore because the original founders of ACADS sold the business, and so the new owners are not running those programs, but there is support available online if you need it. Or talk to your colleagues. I mean, we've all been using Camel for years, so we all know a bit about it, but we can't claim to know everything. So you might have to talk to ACADS. They'll talk to you on the phone, but there is online support available.
I actually had a question, if that's okay.
Yep.
Because I was just chasing ACADS about, they just finished a one-day course back in Feb. And my impression, unfortunately, they're absolutely hopeless. They don't respond very quickly. They don't know if they're going to run any more training. So my question is, or two questions. One, do you know any other places that provide camel training? And the second question is, from your experience, do you think camel is user-friendly enough? If I sign up myself and play with it, I would be able to kind of progress in kind of teaching myself.
Yes. Oh, definitely. Yeah. Look, it takes a bit of getting used to, but there is data available. We used to call it the Camel Driver's Manual. There is a manual that takes you through all those steps, but that's available online as well. I forget what they call it, but the Camel User's Manual, I suppose it's called.
Yeah.
That takes you through all those screens, but also when you're in Camel in the program, you can right click on things and it'll tell you how to sort that out, or how to understand what they want you to put in there. Look, we've had experience with it, a lot of experience, and but we're not really licensed to train people in Camel. We could help you. If you don't have colleagues with a lot of experience in your office, I'm sure that if you spoke to Philip, one of our directors, you could probably arrange to get some assistance with that. We could sit down with you 4 hours. I can remember one engineer started work with us, and he came from overseas. He never used Camel before. I sat with him for maybe 4 hours, and he was right after that, because he just needed to get started. And there'll be things you come across as you work through that you might need some help with. So you can call us. We might be able to help you. Or,
because like I said, I tried communicating with ACADS, and it was a nightmare. It was an absolute nightmare.
Okay.
Yeah.
Oh, I'm sorry to hear that. I mean, they used to be terrific. I haven't dealt with them for quite a few years actually, but before they sold the business, you could call a fellow called Murray Mason or Trevor Kingston. They wrote the program, and they would, as long as you're a licensed user, they would help you solve whatever your problem was. And Trevor was the guy who used to go around doing the training, and he was great. He'd sit with you for a day and go through some examples. You can ask him questions, and he knew all the answers because he wrote the program.
Yeah.
Those guys, they've retired, so things have changed. But there is help. There is help available, and there's plenty of people who've used it. And look, we'd be able to help you if you need that.
Okay.
Yeah. Okay. Now, I've also mentioned here the heat loads can be calculated manually. I'm just mentioning this because I don't think you're going to do that, because it'll take you a long time. But when I started work, which was back in 1980, we didn't have a computer program for calculating heat loads. It was all done by hand. So we had to refer to, in those days, ASHRAE, actually, which was a Northern Hemisphere document. So it was a very long process. But the Aero Design Guide DA09, I'll just show you. I've mentioned all these these are called the Design Application Series. these are fantastic manuals for information on all sorts of things, but DA09 is the air conditioning load estimation manual, and it's got a chapter on psychrometrics as well. If you want some background on heat loads, DA09's got everything. And basically, the stuff in Camel has come out of DA09. There might be some stuff taken out of ASHRAE, but basically it's all there. It tells you how to do it, and it goes through the psychrometric process in great detail. So if you haven't got that, I recommend you get it, because that'll be a good thing to have on hand as well to help you through the heat loads if you're struggling with something. Okay, we'll keep moving. I'll mention here in the highlighted comment there. When you're doing a heating load, generally we call it heat loads, but there's cooling loads for cooling capacity, heating loads for heating capacity. You don't give any credit for internal loads, so you just ignore people, lights, etc. You're just concerned about the heat losses from the space to the outside, and the outside air, and any infiltration. Infiltration, while I bring that up, is a difficult one to estimate. Buildings these days are pretty well sealed, so you don't get much air leaking in, and generally they're pressurised as well, so you tend to push the air out, but usually there is an allowance in Camel. If I go back to this design criteria, I think they mentioned somewhere, oh yes, in this box here, infiltration they've allowed 1/4 of an air change per hour around the perimeter areas. So, and they're saying this for a well-sealed building. One thing with Camel, look, I'll come to this comment in a minute. I'll just go through this. Air design, oh, sorry. Okay, heat load input data to be determined includes the following things: project location and building orientation, so you get that from the architectural drawings. Weather data for the project location, again, Camel has that. You can select an area, a location, and it will normally have it, but if it's remote, it may not. So you might find it in the area handbook, or you might have to search online to the BOM for data for that area. You need hours of operation of the building. It's an office building, starts at 7, finishes at 6 in the evening, perhaps. Other buildings might run 24 hours a day. Thermal zoning details and any rooms within zones. So if you know that there's office spaces within zones, you need to put that back in. Your air conditioning concept design, the type of system you're going to use, the floor area and ceiling height. Eamon, could you just turn your microphone off, please?
Yep, sorry.
A little bit of background noise there, sorry. Floor areas per zone and ceiling heights, operating schedules. All this stuff is what you put into Camel. Operating schedules for internal loads in each zone. So, for instance, people might come and go at different times of the day. So it might be really busy in the morning, and then in the afternoon, a lot of people might go out for meetings or things. So you can put that into Camel so that you're not overestimating the load when the load's not there. The same thing might happen with lights. They might just use certain areas of the building for part of the day, and then not use that part for another part of the day, so that all the lights are out, the people are gone, and that should be taken into account because that will affect your heat load. Occupant density per zone, lighting, internal equipment, outside air flow rates for each zone, which might be litres per second per person, or might be litres a second per square metre. External wall thermal performance details, windows, again, very important to get the windows correct. I've highlighted shading devices. Camel has got, as you put the data in for the walls, Camel will ask you if there's any overhangs, reveals, which is where the windows are set back from the fabric of the building, or they have fins or blades sticking out, which show the windows to a certain extent, and adjacent buildings. Adjacent buildings can be really important. Let's say if the building is in a city, say it's in Melbourne, and it's built in, and there's buildings all around it, obviously you're going to get shading from adjacent buildings. So you need to get the information on those buildings and model that in Camel, because that will make a big difference. You don't want to overstate the cooling load or your heat loads in general, because you don't want to finish up with a capacity that's too high. You'd want to try and get it as accurate as you can. And internal shading devices, they may have blinds or drapes. Usually when you do a cooling load, if they have internal blinds, you would allow for the blinds to be closed. But you'll need to state that and discuss it with your client so they understand that that's what you're working on. If you're sitting in a perimeter office and you've got the sun beating down on you, let's say you're on the western side, and in the afternoon, the sun's coming down, it's very hot and very intense. You're not going to sit there with the sun coming through the window. You won't be able to work in those conditions, not comfortably. Plus, you'll get glare, you'll get direct radiation and glare. So you put the blinds down. That will make a difference to the heat load, because some of the solar radiation will be reflected by the internal blinds. The heat is still coming in, you've still got conduction, but you will reflect some radiation, which will make a difference and make it more comfortable for you to work and will affect the heat load. Roof thermal performance details, floors, internal partitions, allowances for infiltration. Now you can look up, if you're not sure about that, have a look at DA09, have a look at ASHRAE, or the air handle. There'll be something there which will give you a guide, but you can never be sure. It really depends on pressure differential between outside and inside. Is it windy or not, etc. So it's hard to estimate, but there are some guides available. Now, Camel will also ask you for a few extra things like supply and return air duct heat gains or losses. These will, if it's a supply air duct gain, if you've got a long run of supply air duct and it's in a hot space, say the ceiling is hot, it's got a roof over it, there will be some, depending on the insulation, there may be some heat gain to the supply air being delivered to the room. That will affect the room psychrometrics, and we'll talk about that next time. If it affects the return air, if the return air duct is picking up heat on the return air to the cooling coil, to the plant, then that's that affects the coil performance. So we'll have a look at that when we do psychrometrics. The safety factors. Just be careful with safety factors. Camel will ask you to put safety factors in for a few different things, and for the total load. Now, if you just whack in 10%, you need to be careful, because you don't want to, as I said before, you don't want to oversize your heat loads too much. In your initial run, you might put it in just to get an idea of what it's going to be. But try and refine that safety factor. When you're confident with the data you put in, try and refine it, because don't make it too big. Because Camel, through the process, and it won't tell you this, but through the process of calculating things, there is safety factor in Camel anyway. So if you add another 10%, all you're doing is making it bigger than it needs to be. Just be aware, and when you're putting in safety factors, not to overstate it. So the output, Camel program provides a variety of output data. In particular, It'll tell you the cooling and heating loads for each zone and the total capacity required for your air conditioning units and for the plant. If you've got chillers and boilers or DX plant, it'll give you all that. It'll give you supply air, return air, and outside air flow rates for each zone. It'll tell you the resulting temperature and humidity for each zone. So you can look at that and say, well, yep, that's okay. It's aiming to achieve the design temperature that you've asked for, but it may not be able to because of the loads in the space. This becomes a very complex psychrometric analysis, but Camel does all that, and it'll tell you if there's a problem with the output. It'll tell you the mixed air conditions, which is the air entering the cooling coil or the heating coil. So it's the return air and the outside air mixed in their respective quantities entering the coils. It'll give you a psychrometric chart showing you the process. So once you're familiar with the psychrometric chart, so I don't know how much you've done with those, but we're going to talk about them in the next session. They're very powerful and very helpful to analyse what's happening. And they become even more powerful when you get into more complex projects. Like a simple project like a DX system, you probably don't even need to look at the psych chart. It's not going to help you much. But if you're dealing with a complex project such as let's say a museum, a laboratory, which has got cooling, dehumidification, and other things going on, they're very helpful. Now, load check figures, which I mentioned before, watts per square metre or litres a second per square metre. Again, they become useful. So these are the figures we looked at before. These here. When you get your answers, Camel will tell you that the results on average give you 200 watts a square metre. Is that appropriate? Do you think that's right? If it gives you 70 watts a square metre, is that right? Probably not. So it's going to be somewhere in that range. You know, if it's an office building, if it's 150 watts a square metre, that might be okay. It really depends on the proportion of perimeter zone to centre zone. Centre zones will always be lower because they haven't got the influence of the windows and the walls. So you might expect 100 watts a square metre. If you've got a very large centre zone and only small bits of perimeter zone, then the figure should be closer to 100. If you've got a lot of perimeter zone and a small internal zone, then it might be 150 or more. And then you can say, well, I think it looks like the right answer. But if you get some silly answer like 300 watts a square metre, well, there's going to be a problem with the input. You need to find out what you put in incorrectly and fix that. And it provides other useful data, hourly load tables, for instance. I've mentioned psychrometrics. The hourly load tables can be quite useful. And as for every hour of the year, it'll tell you what the load is. So if you want to have a look, Camel will tell you when the peak load occurs. So let's say it's for a west zone, it's going to be in the afternoon in summer, obviously, maybe 4 or maybe 5 o'clock in the afternoon in December or January. But if you want to look at the loads either side of that time, so you want to look at 12 o'clock or some other time, it's all there. And sometimes that's quite useful to know what's happening. And it might help you make a decision about what you select as the maximum load, because you might say, well, really that's not the time that I want to concentrate on for whatever reason. I can't think of a good reason at the moment, but sometimes it's useful to refer to that data. The next session is going to be psychrometrics. So I'm going to, I've already issued these notes, so I won't issue them again, but that's what we're going to talk about next week. So any questions on heat loads?
Maybe just a quick question. let's say you have an office tower, 10 levels. How do you approach designing, whether on camel or manually? Do you treat the whole building as one, or do you, let's say, take every level as a zone, or
Well, typically you'd look at every level, but if the levels are all the same, if you've got typical floors and they're all the same initially, then you don't have to put the data in for every floor. Really, you can you can copy the data from one floor to the next, because Camel has to sum up the total load for the whole building. So you can put the data in for one floor and then just copy it. Camel gives you the facility to copy one floor to the next. So let's say second floor, same as the first. Third floor, same as the first, etc.
Yeah.
And then it will add them all up. You don't want to leave floors out because your total load will be wrong.
Yeah.
Does that answer your question? Or
Yes, it does.
yeah. So you have to do the whole building.
Yeah.
But you can save time by copying data if it's the same. And the same with zones. If you've got zones on floors, you might have some zones that are the same as the previous one. So the first zone's the same as the next one. The first zone goes in, the second zone's the same as that, and the third zone's the same, and so on.
Yeah.
You can just keep copying them. And there's like a tree in Camel where you can just move things. It's like a drag it from one spot to another and just keep adding them on.
Yeah. Okay. And
you'll get used to that when you're using it.
Yeah. And when you designed, add up the whole building, let's say it's 500 kilowatts, for example. I don't know if that's something we'll discuss later. Do you select your equipment based on 100% of that load, or is there, I can't remember that factor where you actually select less because
So you're talking about diversity?
Yes, that's the words. Yeah.
Okay, so diversity is another thing that it's a bit arbitrary. It requires experience and discussion with your client. So for an office building, it really depends on how they use the building. If they're going to be coming and going all day, then your diversity might be, let's say, 70%. But it also depends on how you put the data into Camel in the first place. Because if you've allowed for people to come and go and for areas to be turned off, then that diversity is sort of built into your calculation.
Okay.
But yes, all buildings will have some diversity. Hotel rooms, for instance, if you do a hotel, people who are staying in a hotel are either there usually for business or pleasure. They don't live there. They're not, and so during the day they've gone off to do business or they've gone off to enjoy the place they're visiting. So there's no one in the hotel rooms, generally speaking. And the lights are turned off. The lights should be turned off, and in most hotels they will turn off automatically when you leave the room. The lights are off. There's no one in there. The only load might be coming through windows in the wall, and they might have the curtains closed while they're out. So it's difficult to know what's happening during the day. But so I've done hotels where we've applied a diversity factor of 50%.
Wow. Which
is pretty extreme, but that's how it was, because the management of the hotel said, well, look, really, we probably wouldn't have 50% of the population in the hotel during the day. And smart hotels, we put the card in the door. When you go out of the room, everything switches off. So, and the lights are off. It's only lights and people and fabric loads. So, yeah, that's a good question. It's one of those things you need to analyse and make some judgment on how it's going to operate.
Yep.
Anything else?
I've got a question. So
Yep.
when you're doing the model and you're putting an input for the infiltration rate, would you always use the default value of 0.25 air changes for infiltration, or what factors can you think about to customize that value?
Good question. Again, that's a difficult one. And there's a few of these things that they don't amount to much in the total heat load. So it's not critical, but you do need to put something in there to make allowance for it. I think in a modern building, 0.25 is probably a good number to put in there. Again, this is like another safety factor, because if the building is pressurized, you may have almost no infiltration at all. Okay, so if it's a modern building that's got good sealing, and it's a requirement of building practices these days to seal buildings very well, and usually the outside air coming in, look, if we talk about an office building, the outside air is greater than the exhaust. So you've got some pressure, positive pressure in the space, which is going to prevent leakage anyway. So by putting in infiltration, it's another safety factor. So I think don't oversize it again. 0.25, if you want to put something in, put it in. If it's an old building that's got old rattly windows and things like that that might leak, then maybe you need to allow half an air change an hour for leakage. But there are in DA09, I'm not sure exactly where, but there are, I think it's in, well, it's obviously in the heat load section. I can't remember which chapter it's in, but I'll find it and let you know. There is some guideline on what to use for infiltration. But again, it's not gospel. It's not a real thing. It's just an estimate, just an allowance.
Yep. Okay, thanks.
Okay. Anything else?
Nope.
Okay. Well, I'll just finish by saying it's been a very brief introduction, and it's a big topic. Putting data into Camel takes a bit of time, but it's better to spend the time and try and get the best accuracy you can with the data you put in. Once you've got the data in, it's very easy to change things. So get some data in there, even if you're not sure the first time. Put something in there, but make sure you know what you've put in that needs to be checked, and you can get your data in and run a heat load and get your first pass to see what it looks like. But then make sure you can get the correct data in when you can. It's very easy to put it in and very quick to run the calculation again. When Camel first came out, which was in the 90s somewhere, mid-90s perhaps, we did a hotel with Camel. It took, well, we had a lot of zones, but it took a fair while to put the data in. But in those days, I don't know whether you've heard of a 286 computer. That's all we had. We had to put the data in and let it run all night to get a result. And so we got back to work in the morning and we had a heat load. And then we thought, we've got some mistakes. So back in again, and then ran it at night and had some results the next morning. And then we thought, no, this is no good. We need a bigger computer. So we got a 486. And that did it in about 15 minutes. And then we thought we still weren't happy with that. So we bought what was it? Anyway, we upgraded again and it did it in a flash. So these days you've got the benefit of getting results very quickly. Even for big projects with a lot of zones, you'll get a result very quickly. And you can change the data quickly and run it again. So it's great. But as I said, you can do manual calculations. It'll take you a lot longer. It'll take you weeks for a decent sized building to put the data in and do the calculations, or to do the calculations. But DA09 is a very useful reference, and I recommend that you get a copy and have a look through it and see what's there, because it is very helpful. If you get stuck on something, DA09 can help you. If the camel driver's manual doesn't give you the answers you want, have a look at DA09. Okay.
All right.
Okay.
Thank you.
Thank you.
Thank you.
Okay, thanks.
See you next time.
See
See
you.
ya.
Yeah. Bye.